Hi everyone, welcome back to the last of our discussions about Newton's laws. Or at least the last of our discussions about Newton's laws in this particular unit. In fact, this might be the most important of our videos among the problem-solving videos, which have involved the last three, including the current video. So here we're going to take a look at friction and how to deal with problems that contain friction. So let's consider friction. Friction is a resistive force. It's something that tends to resist any change in, something that tends to resist an object moving with respect to a particular surface. So, of course, if the surface is moving, then it would cause the object to want to move. But if we consider our reference frame to be the surface itself, friction is going to act against the motion of any object on it, assuming that the object feels the friction. How does an object feel the friction? Well, the degree to which an object feels the friction is something called the coefficient of friction. It's a dimensionless number, meaning that it has no units, and it's defined as the ratio of the friction force on an object compared with the normal force. So if you need to calculate the friction force, then you just multiply the normal force by this parameter called the coefficient of friction, which is symbolized by the lowercase Greek letter mu here. It's kind of like a U, but a mu has a little tail on the left side. Now, coefficients of friction are properties of the materials themselves, and they have to do with the two particular materials that are interacting. Each of the materials is important for determining what mu is. For example, the coefficient of friction between rubber and ice is going to be very different than the coefficient of friction between rubber and asphalt. And similarly, the coefficient of friction between ice and rubber is going to be very different from the coefficient of friction between ice and metal. So, things that we think of as, quote, sticky, have a high value for the coefficient of friction. It requires a considerable force to move something that is sticky sideways across a sticky surface. Now, what about these coefficients of friction? They are properties of the materials, so they are parameters that need to be determined experimentally. In some cases, they can be determined experimentally using elementary experiments, as we're going to see soon. In other cases, you just kind of need to look them up in a table in order to be able to solve some other kind of problem. So there are two types of friction that we're generally going to deal with. There is kinetic friction, where the two surfaces are moving with respect to each other, meaning they're sliding. And then there is static friction, where the two surfaces are at rest with respect to each other. Keep in mind that when objects are rolling, the point in contact is at rest, so when a car is hitting the brakes but not skidding, that's actually static friction there, because the point of contact between that particular part of the tire and the road is at rest. It's just that it's a different part of the tire at each instant as the tire itself rotates about its axle. So we're going to not generally do calculations with rolling friction here. Rolling friction is caused by the circular surface itself, or the circular object itself, being a little bit deformed by its contact with the surface and or causing a little bit of deformation in the surface, but we're not going to be dealing with that so much in this class. Now, static friction is generally stronger than kinetic friction. So the result is that coefficients of static friction are generally higher than coefficients of kinetic friction. You know this by experience. It's usually harder to initially budge an object than it is to keep it moving after you have already knocked it loose. Here's a table of some coefficients of static and kinetic friction. We might have better values for some of these now. This is a relatively old table, but still you kind of get an idea. Things that you would think of as being slippery have low values of coefficient of friction. Things that you would think of as being either kind of somewhat sticky or actually truly sticky, like Velcro, have high coefficients of friction. Generally speaking, something that has a coefficient of friction of close to 1 that's a high coefficient of friction. That's quite high in terms of friction. Now, as a quick example, consider a 5 kilogram pane of glass resting on a large fixed pane of glass. So calculate first the horizontal force necessary to begin to move it horizontally, and then second, the horizontal force necessary to keep it moving horizontally at a constant, non-zero velocity. So first, let's take a look at the free body diagrams for this. To initially budge the pane of glass, we're dealing with the situation on the left, where we represent the glass by a dot. There's weight downward, there's normal force upward, and let's say we're trying to budge it to the right, so we apply a force to the right, and at the instant just before the instant where it breaks loose, the force of static friction toward the left is equal to this applied force on the right. Now, the instant after it breaks loose, suddenly the friction to the left goes down significantly and becomes kinetic friction. And for a moment, you're going to have that previously applied force acting on it, and it's going to jerk loose. We're going to examine that jerking process soon. But after it's jerked loose, the friction is now kinetic friction, and you have, therefore, a smaller applied force in order to keep it moving horizontally at constant velocity. And notice that from diagram to diagram, the normal force and the weight remained unchanged. After all, it is the same applied force. Or sorry, the same object, the same pane of glass with a mass of 5 kilograms. Now, what about the actual calculations? Well, to initially budge the glass pane, write out our givens. We have a mass of the glass pane, a coefficient of friction. So, at just the limit, just before it budges, the net force in the x direction is 0. Now, something to keep in mind is that force of static friction is a maximum force of static friction. Before you start pushing on the glass pane at all, there's no static friction acting on it at all. If you push it with just a very tiny force, there's going to be a very tiny static friction force opposing your pushing. As you increase the applied force, the static friction force becomes larger and larger until you reach the point of the maximum static friction force, which is calculated by taking the normal force and multiplying by the coefficient of static friction. So yeah, when you do static friction equals normal force times coefficient of static friction, that's the maximum possible static friction force. But if you're pushing on it and it's not moving, that's because generally there's static friction acting against you. But once you break loose, then it becomes kinetic friction, and that's actually a fixed value. No matter how fast it's moving, if it's sliding on the surface, it's the same amount of kinetic friction. So, in any case, in the x direction, just before you nudge it loose, or budge it, or break it loose, the acceleration in the x direction is 0. So Newton's second law says the net force in any direction is equal to the mass times the acceleration in that direction. Well, what is the net force in the x direction on this glass pane? Well, going back, we have the applied force in what we're going to call the positive direction, minus the static friction force in what we're calling the negative direction. So, that's 0. The total of those is 0. So therefore, the applied force is equal to the maximum static friction force. Well, what is the maximum static friction force? Well, we know that the equation for static friction, or any type of friction, is equal to coefficient of friction times normal force. Well, normal force isn't in the horizontal direction. How do you figure out what normal force is? We use the vertical direction in this case, since it moves either horizontally or vertically. The horizontal surface, the surface on which it could potentially move is horizontal. So in the y direction, well, net force in the y direction is mass times acceleration in the y direction. That's 0. So normal force minus weight equals 0, because in that free body diagram, the normal force goes up, the weight goes down. So therefore, the normal force is equal to the weight. Well, I have an equation for weight. That's just W equals mg. So now that we have that, we use the fact that the normal force is equal to the weight to say that the maximum static friction force, because after all, friction force is equal to coefficient of friction times normal force. Oh, I got the normal force by looking in the y direction. That's W equals mg. So I plugged in mg for my normal force there. So, therefore, that maximum static friction force is mu sub s times mg. Well, we just established that that's the amount of applied force that I need to give in order to break this pane of glass loose. So my applied force is mu sub s times mg. We're ready to plug in the numbers, and upon doing that, we get 44.1 newtons. What about the amount of force necessary to keep the glass pane moving after you've already dislodged it? Moving at constant velocity, that is. Well, we have the coefficient of friction now is 0.4. So it's the same analysis as before, so I'm not going to go through the details of it. It's exactly the same as what we did for the glass pane to get it moving in the first place. But now we simply have kinetic friction instead of static friction, and it's a coefficient of kinetic friction. All the math is the same. We just plug in a different value for the coefficient of friction. We plug in 0.4 this time instead of 0.9. So now the amount of applied force necessary to keep it moving at constant velocity is 19.6 newtons. Okay, well, what about that jerk that happens right after you dislodge something and then you try to move it? Well, it doesn't just barely dislodge. A lot of times it will pop free and jump a little bit. Well, that's because it's undergoing an acceleration. Why is it undergoing an acceleration? Because you are still applying the same amount of force on it that you had been applying to try to dislodge it. But at the instant that it dislodges, the opposing force is no longer static friction. The opposing force becomes the smaller kinetic friction force. So here's the free body diagram for that. Here, at the instant that it dislodges, your applied force is the same as what had been the maximum static friction force, but now you're dealing with kinetic friction. So what do we do here? Well, we do the same thing as before. The force in the net force in the x direction equals mass times acceleration. So we've already calculated these net forces though. So we could just plug them in right now if we wanted. So here we noted that we're plugging in the fact that the friction force is equal to the coefficient of friction times the normal force, which in here I'm just calling lowercase n. So therefore, the acceleration, which is always equal to the net force divided by the object's mass, is just equal to that expression that we just got for the net force. So factoring out a normal force, and I want to be consistent in what I'm calling my normal forces. I want to call them lowercase n, so I'm going to tell PowerPoint to fix it, and just like that, it's fixed. So in this case, again, we just started with Newton's second law, solved for acceleration, and plugged in the net force that we got from before. So now, plugging in normal force equals mg, because it's the same situation as the problem before. We already solved for the fact that normal force is mg. We notice that our masses cancel, so in this case the acceleration is independent of the mass of the object. Once you get it broken free, it's going to have that same instantaneous acceleration until you make the applied force equal to whatever is necessary to keep it going at constant velocity. So then, now that we have our equation, we're ready to plug in numbers. Mu sub s is 0.9, mu sub k is 0.4, and upon doing that, we get that the object's instantaneous acceleration is 4.9 meters per square second. And it's going to accelerate that until we kind of let up on how much force we're using to try to dislodge the object, now that it's already moving. Okay, how about another problem? How about a book sliding across a horizontal floor? Well, a book sliding across a horizontal floor is eventually going to come to a rest. So, calculate the coefficient of friction between the book and the floor if that book experiences an acceleration that we're going to call a. Well, consider the free body diagram. Here we're going to assume that the book is actually sliding to the left, but that would mean that the friction force is acting on the book toward the right. So, with that in mind, we have that friction force is equal to mu times the normal force. So mu is friction force over normal force, but the friction force is the only force acting in the horizontal direction. Maybe I should have been a little bit more explicit. I should have said that friction force, or net force, equals ma, but I see this to some extent as kind of the same problem as before, so it's like we already did that step, but if you're doing a test, you should write it explicitly that net force equals ma, and then that the net force is equal to the kinetic friction force. So kinetic friction force equals ma, but as we analyzed before, and again I should probably state that directly here, net force in the y direction equals may, but a sub y is 0, so net force in the y direction, which is normal force upward minus weight downward, is equal to 0. So if n minus w is 0, n equals w, so therefore n equals mg. So I plugged in mg for my normal force. But the masses cancel, so this tells me that in this experiment, the coefficient of kinetic friction between the book and the floor is just given by the acceleration divided by the acceleration due to gravity. This is an extremely useful result. This has direct practical applications if you're trying to either figure out the coefficient of friction between two materials or what the acceleration is that you should expect when you slide something across a floor. Well, let's consider this in terms of numbers. If you've ever played the game of keys, that's where you're, say, at one end of a long hallway and you and a bunch of friends try to slide your keys to the opposite end of the hallway, and the winner is the person who gets their keys the farthest without actually hitting the wall. If you hit the wall, you're out, but the person who gets their keys the farthest without hitting the wall is the winner. And theoretically, you're supposed to do it at the same time so that you can't make adjustments or just toss your keys downward after everybody else has struck out. So, in any case, in this game, consider a set of keys that has traveled 27.6 meters before coming to a rest after a time of 4.02 seconds. And here, the idea is that you started the stopwatch at the instant that the keys entered a certain spot from which you were able to measure a distance of 27.6 meters, and you stopped your stopwatch after the keys came to a rest, and then after that you went out and measured the 27.6 meters. Calculate the coefficient of friction between the keys and the hallway floor. And here we're talking about kinetic friction. So here is our free body diagram, same thing as before. Our givens, distance of 27.6 meters, a time of 4.02 seconds. So the net force in the x direction is equal to mass times acceleration in the x direction, but I'm just going to call that acceleration. But there's only one force in the x direction, the kinetic friction force. So F sub k equals ma. Okay, great. Well, F sub k I know is equal to mu sub k times n. So all I need to do is figure out what n is. Well, the net force in the y direction is 0 because the keys aren't jumping off the floor. The keys aren't disappearing into the floor, I hope. So that acceleration is 0. Well, the net force in the y direction, well, let's see. We have normal force upward minus weight downward equals 0. So therefore, the normal force equals weight, which, by the way, is mg. Make sure to memorize W equals mg. It's very useful. So with that in mind, we plug in mg for our normal force, because that's what it is in this problem. We just figured that out. So now we say, okay, F sub k equals ma, F sub k equals mu sub k mg. We can set those equal to each other. And notice again, the masses cancel. Oh, surprise, surprise, mu sub k equals acceleration divided by acceleration due to gravity. Same thing we got in the previous more general example where we didn't show all of our work. What about that acceleration? How do we get the acceleration? So here's what comes to mind. We think about a situation where, say, we start an object at rest and we allow it to undergo constant acceleration. Well, in that case, delta x equals v naught t plus 1/2 at squared. Well, if it starts from rest, then we just have delta x equals 1/2 at squared. But this is exactly the reverse of the situation of starting it at whatever velocity it had at the end, which we don't know, it's not part of that equation, and allowing it to come to rest because of that same acceleration. After all, parabolas are symmetric, and if you were to make a position versus time graph of something like this, it would be parabolic. So instead, we're going to think of this just as the time reversal of starting something from rest and allowing it to accelerate at constant acceleration until it reaches a certain distance at a certain time. Well, it's the same thing here. if you made a video of something like this, and then you played the video in reverse, it would undergo constant acceleration starting from rest and go that same delta x in that same amount of time. So it works. So solve for the acceleration, and you get 2 delta x over t squared. And we're going to plug that into our acceleration from our formula for kinetic friction that works for this problem. So we plug in the a right there, and here's our equation. And now, we've been good physics students, we've derived our equation in terms of variables only first, and now we're ready to plug in our quantities with units. Notice the second squared cancels, notice that the meters cancel, and we're left with a coefficient of kinetic friction of 0.349. Notice it has no units. So that's how you can obtain the coefficient of kinetic friction between two materials by sliding one across a horizontal surface composed of the other material. And that is the last of our examples with friction, and indeed the last of our discussion about Newton's laws, at least for this unit. We will come back to Newton's laws in the next unit where we talk about circular motion, because analyzing the motion of objects undergoing uniform circular motion involves understanding Newton's laws. So hopefully I will see you then, and thank you for watching.